Hello students, welcome back. So we were doing atomic structure and by this time we have already discussed many of the sectors of the atomic structure regarding the orbit diagram, regarding the electronic configuration, how to draw the electronic, go with the how to write the electronic configuration, draw the orbit diagram, and we have also discussed regarding the capacity of orbits and the history of the structure of the atoms and the discovery of the subatomic particles. Many things we have already discussed. Today, in this class, we are going to discuss about the existence of atoms in different forms. Forms means they will be classified in terms of, or rather I should say grouped, in terms of the count of subatomic particles. More or less, I should specifically say, not also subatomic particles, but specifically the count of nucleons. Right? We all know that what are nucleons? What is actually nucleons are? So in simple words, these are basically particles present within the nucleus of an atom are referred to as nucleons. So proton is one of the nucleon, neutron is one of the nucleon. So based on the count of these nucleon, depending upon the count of these nucleon, the classification or the grouping of atoms has been done. So let's move on to those classifications. What are the different groups or categories into which the atoms have been classified? These are the broad three classifications, or the three major classifications. Definitely, but there are no such minor classifications. These are the major, these are the classifications based on which I shouldn't say based on which, in other words, I should say that uh, it has been classified in terms of the nucleon count. These are the three groups into which atoms have been classified or grouped in terms of the proton count as well as the neutron count. So the first one is the isotopes, second one isobars, and the third one isotones. So definitely we are going to discuss each and every uh, three classic classes or groups of these atomic classifications individually. Then definitely the idea about what it is all about, these particular classes or groups, what do they suggest, what information do they provide, everything will be clarified. So we can start with isotopes. So obviously every time I put up this question, and I definitely want all of you to move on like that way, that whenever you will find across or come across, whenever you come across a new word, whether it's any, it is related to whatever the subject doesn't matter. But whenever a new word you are coming across, you should ask the very first question, what's the meaning of that? So if I follow that particular question, and looking at this word, what is the meaning of this word? Obviously, I go with the definition first or the meaning of this word first. Isotopes are actually atoms who are having the same atomic number, a different mass number. This is the definition of an atom. I can represent this atom, or rather this definition, in other words, in a more, this is a most simple word, but if I want to make this one, if I want to see this isotopes from the point of view of the subatomic particles, then definitely I have to explain this. I have to represent this definition in terms of the subatomic particles. So what I can say, atoms having the same number of protons, a different number of neutrons. As I said earlier, that these classes or groups have been made in considering the neutron and the proton count. So electrons are having no role in this particular, or rather in these classes. So in these groups, electrons have no role or no contributions in this particular in this particular definitions or classes or groups. So now I would move on with the definition, and that is from the point of view of subatomic particles, especially the nucleons, that atoms having the same number of protons but different number of neutrons. And definitely, whenever we give a definition, examples are must. Examples are must. So, when an atom is having same number of protons and different number of neutrons, considering that we have been having three different atoms, Q, R, S, and different atomic numbers and different mass numbers have been assigned. Z1, Z2, Z3, and A1, A2, A3. Now, the Z1, Z2, Z3 are the corresponding atomic numbers and mass numbers of QRS. Now, there can be certain conditions. The first condition is, what if Z1 equals to Z2 equals to Z3 and A1 equals to A2 not equal to A2 not equal to A3? What does that mean? This means the question is, as it's written over, what does it signify? What does it mean? It means that the atomic number in all the three respective atoms, that is QRS, the atomic number remains the same and the mass number varies, which means the number of protons present in Q, atom R, and atom S, the number of protons in all the three atoms are the same. And the mass number different means the number of neutrons in all these three atoms are different. Hence, we can conclude that it is basically one single atom. It is basically an atom of the same element because the number of protons in all the three respective atoms, which were initially considered to be different, P, Q, R, S, are actually the same because the number of protons in all the three atoms are same. And since they are same, hence they represent the same element. So they are basically the same element, atoms of the same element, but existing in a slightly different form. They're having the same chemical properties, but in terms of physical properties, there are slight differences. Clear, everyone? So there it goes. Hence, we can say that QZ1A1, QZ1A2, QZ1A3. So all these are isotopes. And since over there it's written Z1 equals to Z2 equals to Z3, so we can substitute Z2 by Z1, we can substitute Z3 by Z1 also. So hence, this represents that all are the same atoms, different mass number, but same atomic number. Now, after the general examples, it's time for the real examples of isotopes. The first example that comes within our minds, that is, we start every time with hydrogen, because that's a very, very common example for isotopes. So we are having H, that's the symbol of hydrogen, 1, 1, with the atomic number at the subscript and the mass number as a superscript. As if you remember, as it was symbolized earlier. As it was symbolized earlier regarding that when Q, R, and S, you can check it if you remember that it was the Z at the bottom, at the base, and the air symbol was at the superscript level or the top. So exactly like that way, it's the mass number at the top and the atomic number at the base and the element symbol in the middle. So H11, H12, and H13. So these are very common. This is one of the common examples of real examples of isotopes. Interestingly, these isotopes are having names, and those names are written over there as protium, deuterium, and tritium. Interestingly, this hydrogen isotopes only are having names protium, deuterium, tritium. The rest, there are many isotopes. It's not that only hydrogen is having isotopes. It's not the fact. There are other elements also which are having isotopes. Like me, for example, if I continue with giving examples of this one, we're having C612, C613, C614. And it's written as carbon 12, carbon 13, carbon 14. We do not write carbon 666 because over here, since the atomic number is constant, so there is no point of writing carbon 666. We are mentioning carbon 12, 13, 14 to where the atomic masses have been highlighted. Because atomic mass varies over here with isotopes, atomic numbers are same. And since we are writing the name of the element completely, as a complete name is mentioned over there, that's carbon, carbon, carbon. Hence, there is no point of mentioning or to highlight the atomic numbers specially along with that. Rather, it will be better to highlight the atomic masses because that's the point of variety. That's the point of distinction between all the three different atoms. Though the atoms belong to the same carbon element, but there is slight difference because the number of neutrons are different. Coming to another example, we are having oxygen, O816, O817, O818. So oxygen 16, oxygen 17, oxygen 18. Another example of isotopes we are having, very common, very popular, chlorine 1735, 1737. 1735 and 1737. Very popular. Now, this is once again a repeat, which I told you earlier also, that is, these are not the only elements which are having isotopes. There are other elements also which are having isotopes, and don't ever think the isotopes numbers are restricted to 2, 3 only. There are elements which are having isotopes more than 10, 15, even 26, 30 isotopes. So there's a bunch of isotopes which other elements are having. Okay? So this is all about isotopes in precisely and a much more informative way. Now it's turn to switch over to our next category. And our next category is isobars. Isobars are our second category, second section, isobars. Alright, let's begin with isobars. Once again with the definition first. We are having atoms having same mass number but different atomic number. That means now the atomic number will be different. That means the proton count will be different, but all will be having the same mass number. What does this mean? Can this be written in a different way? No. Can I express this one in any sort of similarity in terms of protonic or neutronic count, nucleon count? Nucleons collectively there is a similarity, but individually there is no similarity because mass number is same. Considering this fact, I accept this fact, but if you also need to consider that the atomic numbers are different. So atomic numbers are different. Though the mass number is same, the number of neutron counts will also come different. The number of neutron count will also come different, and hence they are called isobars. Once again, moving on to a general example, that is considering the same one represented A1, Q Z1A1, R Z2A2, and S Z3A3. And we all know that what A1, A2, A3 are and Z1, Z2, Z3 are of the corresponding atoms of the elements Q, R, and S. The condition number 2 now. Before, if you remember with the isotopes, we discussed about condition 1. Now it's condition 2. What's the condition? What if Z1 not equal to Z2, not equal to Z3, and A1 not equal to A2, not equal to A3? Then what does it signify? It signifies that when the atomic numbers are different, that means it's clearly indicating that the atoms does not belong to the same element. Though the fact is the mass number or the atomic mass of the individual atoms remains same. That means same in terms of equality. So all three atoms have the same atomic masses, but the num atomic number remains different, which reflects the number of proton does not match in any of the atoms. Right? So they are not equal. Number of protons are not equal in all the atoms over here. That is Q, R, and S. All are different. So the neutrons will vary, the protons are varying, but the similarity is collectively the nucleon count to total, protons plus neutrons, collectively to a total, the result comes out to be the same. Definitely now we are going to move on to we will discuss certain examples, and we know that always we need to give examples when we are discussing about any sort of definition or any other situations in the whether it's physics or chemistry or biology. So we need to give examples. So Isobars real examples. First, argon 1840, potassium 1940, calcium 2040. So you can check it out. That's in all the three atoms, the mass number remains same, 40, 40, 40. But the atomic numbers are different, 18, 19, 20. Atomic numbers are different. The second example, we are having carbon 640, nitrogen 740, boron 540. So all the atomic masses are same, but the atomic numbers are different, 6, 7, 5. They're different. Phosphorus 1531, sulfur 1631, silicon 1431. All the mass numbers are same, but atomic numbers are different. So P phosphorus, S sulfur, Si silicon. Iron Fe 2656, Mn 2556, and CO 2756. In all the once again the atomic masses are same, the mass numbers are different. In connection to the atoms of the individual elements, or respective elements, they are the iron, element iron Fe, element manganese Mn, it's 2556, and element cobalt 2756. So all these are isobars. Okay. Now it's time that we should move on to our third category. What was our third category? Isotones. Isotones was our third category. Now, when we're going for isotones, what's the definition? Over here, atoms having different atomic number and different mass numbers, but the same number of neutrons. That's a pretty interesting thing. But over here, we will be having, the definition says that atomic number is different, mass number is different. So two things are different. Previously, atomic number is the same, mass number is same. Now the third case is atomic number is not same, because they are different. Mass number is different, but the number of neutrons in all the atoms, they are equal. So whatever the element is, or whatever the mass number is, doesn't matter. But if the difference between the atomic number and mass number, or rather the mass number and atomic number, the difference between these two values will give us the neutron count, and the neutron count will be same for all the atoms of that particular group. Group means whichever the atoms have been considered for the group. That group should have equal number of neutrons. For example, once again we'll consider the same example, QRS and RZ2, Z1, A1, A2, A3. So what we are having? The third condition. This is our third condition. Third condition, Z1 not equal to Z2 not equal to Z3. That means atomic numbers are different. They're not the same. A1 not equal to A2 not equal to A3. That means the mass numbers are also different. They are also not the same. Then what is the similarity? The similarity is A1 minus Z1 equals A2 minus Z2 equals A3 minus Z3. So that is this value. So A1 minus Z1 gives us the number of neutrons. A2 minus Z2 gives us the number of neutrons again for the element or the within the atom of the element. Uh, what was the element Q R? And A3 minus Z3. A3 minus Z3. That means the number of neutrons present in the atom of element S. So in every time A1 minus Z1, the number and the neutron count within element Q or S are all the same. There is no discrepancy, no discrimination, nothing. Then what does it signify? It means, as I said, that though the mass number atomic numbers are different, but the number of neutrons in all the atomic species are same, which I explained just now. Considering the real examples, the first set is 1636, Cl 1737, calcium 2040. So if you calculate the number of neutrons, that is A minus Z, generalizing expression A minus Z, and if you consider this particular group, then you can find it out that the number of neutrons in sulfur, the number of neutrons in chlorine atom, and the number of neutrons in calcium all are giving the same result, that is 20 neutrons present. Then another example, that is C613, N714, B512. This is the set. And if we calculate the number of neutrons present over here, it will turn out to be 7. So 7 in every situation. So it is carbon 613, that is 13 minus 6 gives 7. N714, 14 minus 7 is 7. And finally B, boron, that is 12 minus 5, that is also giving 7. So you can check it out, that is number of neutrons 7. Now it's time that we should move on to our another set of discussion. And I think before going to that one, regarding isotones, isobars, and isotopes, none should have any confusion after this. No confusion. It should be clear after watching and following this entire lecture up till isotopes. Now we will switch over to another category of discussion, that is valency. A very, very important part in chemistry, that's valency. It plays a very critical role in determining the valency of a place, or place valency is not acceptable, valency of an atom. Very important. So as I say always, we need to go with definition first. The combining capacity of an atom of an element or group of atomic species. The combining capacity of an atom of an element or a group of atomic species. For example, valency of oxygen, that's 2, and valency of hydrogen is 1. Valency of sulfate, 2. Valency of nitrate, 1. Now we have read the definition, we are having examples with us, but still there can be some confusion regarding the statement. That is the definition, that is the combining capacity of an atom of an element or a group of atomic species. Now what does this word combining, the words combining capacity means, refer to? The combining capacity means refers to, that is with how many atoms one particular atom can form a bond or can form a relationship. So combining capacity of an atom means with how many atoms, with how many same atom, or it can be different atoms, whatever the thing is, with how many atoms a single atom is making a bond at a time, or establishing firm relationship at the same time. How many are there. So that those particular number of bonds or atoms actually govern the entire valency section. So valency is actually with how many quantity wise, with how many the bond formation is taking place. The concept of valency is used when atom tries to form a molecule. Of course, it is basically it is valencies for atoms, not from any molecule. Molecule doesn't have any sort of valency. Atoms have valency. So the concept of valency is used when an atom tries to form a molecule. In more simple words, it's trying to say that the capacity of one atom to combine with another atom. Capacity? Yes, capacity. That with how many another atom it will combine, it will form bonds. It can be one atom. That means it can be that it is forming two bonds, it is forming three bonds, or the same atom is forming four bonds also. Depending upon the number of bonds a particular atom is forming, the valency of that particular atom within that particular molecule is being determined and governed. Now, let's consider certain examples. Then it will be much more clear to understand. The first example said we are having the molecules H2O2, H2O, CH4, PH3. We are having these list. So we'll start with hydrogen first. This molecule contains two atoms of hydrogen, right? This molecule contains two atoms of hydrogen. For that reason, H2 written. What does this mean? That is, one atom of hydrogen has combined with another atom of hydrogen by forming one bond. Understand this. We are having two hydrogen atoms. That means a molecule of hydrogen. It's existing freely in nature. Now within that, one atom of hydrogen has combined to form another atom of hydrogen to form one bond. And hence, thus, from the perspective of one hydrogen atom, its valency is 1. I hope it's clear to you why it's 1. Okay. Okay, so now moving on to our second example. We are having oxygen. A second example. This molecule contains two atoms of oxygen. You can see that O2 is written. So 2 represents two atoms of oxygen. So within this molecule, two atoms of oxygen are there, which have actually combined. Remember, the two atoms of oxygen have combined to form this molecule, right? But with respect to one another, they're actually one atom. One atom of oxygen has combined with another atom of oxygen. So one atom is combining with another one atom of oxygen to form a molecule of oxygen. But two bonds are there. When oxygen atoms are combining with another atom of oxygen, so one atom of oxygen is combining with another atom of oxygen, the only thing is they're sharing two bonds between them. Two bonds between them. And hence the valency of oxygen is 2. So the combining capacity when it is in terms of unimolecular system, unimolecular, over here I want to refer to, I shouldn't say unimolecular, that's my mistake. Better to say when it is having one atom, when it is respect to one bond system. So the number of bonds that particular atom is making with one another, that is valency. Over here, one atom is making two bonds, so the valency is 2. So the valency of oxygen is 2 since the atom of oxygen is forming two bonds between them. So the relationship which they are having is being distributed among two bonds. Moving on to our third example. Methane. This is CH4. This is what we call as methane. The name of the compound, the name of this molecule is methane. It's a compound, and the name of this molecule is methane. This molecule is having, you can check it out, 4 atoms of hydrogen and 1 atom of carbon. This molecule is having 4 atoms of hydrogen and 1 atom of carbon. That means, what does this signify? This means that is the carbon atom is is sharing a relationship with 4 hydrogen atoms. This carbon atom, one carbon atom, is sharing a relationship with 4 carbon atoms, or I can say it has combined with 4 atoms of hydrogen. This carbon atom has relationship with 4 hydrogen atoms, and it has, or it I can say it has combined with 4 atoms of hydrogen. Okay, it has combined with 4 atoms of hydrogen, or it is sharing a relationship. This atom of carbon is sharing a relationship with 4 atoms of hydrogen by forming 4 bonds. 4 bonds. Or I can say one atom of hydrogen has combined with one atom of carbon. So this is from the one we have analyzed from the perspective of carbon. You can check it out. That is, one atom of carbon has combined with 4 atoms of hydrogen by forming 4 bonds. That is from the perspective of carbon. And if we're analyzing from the perspective of hydrogen, then one atom of hydrogen has combined with one atom of carbon by forming one bond. Now, when one atom of hydrogen is making a relationship with carbon, from the perspective of hydrogen, carbon is one. So whether that carbon is engaged as forming a bond with any other hydrogen atom, that is not the matter of concern with that particular hydrogen atom. It is just looking into the fact that it is forming one, it can form one bond, and the carbon is there and it is ready, and hence making a bond, no problem in that. And hence, from the perspective of hydrogen, number of atom is 1. Okay, so thus the valency of carbon is 4 and hydrogen is 1. Let's move on to another. Let us move on to another example. This is pH3, phosphine. The molecule is called phosphine. What we can see over here, this molecule contains 3 atoms of hydrogen and 1 atom of phosphorus. So again, we will analyze from the perspective of phosphorus and from the perspective of hydrogen. In the same way, the explanation goes that 1 atom of phosphorus is combined with 3 atoms of hydrogen by forming 3 bonds. Isn't it so? 1 atom of phosphorus is combined with 3 atoms of hydrogen by forming 3 bonds. So phosphorus has formed 3 bonds with hydrogen. A relationship thrice. Okay, so 3 atoms of hydrogen. So, or hydrogen has combined with 1 atom of phosphorus by forming 1 bond. Thus, the valency of phosphorus is 3 and hydrogen is 1. Moving on to another example. FeBr3, this molecule contains 3 atoms of bromine and 1 atom of iron. So 1 atom of iron is combined with 3 atoms of bromine by forming 3 bonds. Now, from the perspective of Br, so 1 atom of bromine has combined with 1 atom of iron by forming 1 bond. So iron making 3 bonds or sharing the relationship with 3 atoms of bromine, whereas bromine is sharing a relationship with 1 atom of iron or forming 1 bond, and hence the valency of iron is 3 and the valency of bromine is 1. Now these are basically valencies of atoms, but there can be valencies, there are sometimes valencies of charged particles also. What's that? For example, for ions, they also have some valency. Sometimes you may notice that in some books it's written that bivalent radical, trivalent radical, monovalent radical. So bivalent radical, trivalent radical, so this word radical is associated with them. So bivalent radical, trivalent radical, all those things are basically associated with ions specifically. So there can be positively charged species, there can be negatively charged species. So now we are having positively charged, negatively charged, all. So how the valency of those species are determined. We are having sulfate. You can check it out that there are for these ions, as I said, the charge of the ions for the valency of those ions. SO4 minus 2, the valency is 2. So always remember valencies cannot be any minus. Valencies cannot be minus or plus. Please do not write this minus and plus. Valencies only write the numerical without any plus or without any minus. Don't write this plus and minus. The meaning will change. So valencies over here, the sulfate for sulfate, you can say SO for 2 minus, the valency is 2. NO3 minus 1, valency is 1. Phosphate PO4 3 minus, valency is 3. Chloride Cl minus 1, valency is 1. So you can write minus or minus 1 meaning the same. So this is how the valency of ions or charged particles are determined. So I don't think it's very difficult or very tough to identify or to make it out the valency of charged particles. But there are possibilities. There are possibilities that a particular element or particular atom can behave differently under different conditions. A same element is combining with the probably I can consider the same atom, but in a different way, different behavior. That means the same element is exhibiting a multiple behavior or showing different sort of relationship with the same atom if the surrounding conditions are different. And hence, such conditions led to the occurrence of variable valencies. So there are elements which exhibit different valencies, as I explained. Means the element will combine or interact with other elements differently, which would result in different chemical behavioral properties. That also I explained just now, and hence exhibits variable valency. So such behavior is called variable valency. Variable valency means same. This is applicable for those for that is same element is showing multiple valencies, more than one valency. If a particular atom is showing more than one valency under different conditions, that means that same element is having different characters. One particular person is showing different characters, and hence don't we say that it is one person is showing is capable. Suppose for a person is capable of playing keyboard, playing guitar. He's also capable of singing. Is a very good dancer, as well as can play chess, and is capable of writing poetry. What do we say that? Don't we say that the person is a multi-talented person, the same person? Do we use this one for a single person, for a person who is doing just one particular job? No, we cannot use that thing. So one person, when is showing such thing, we explain we explain in such a way that it's a multi-talented person. The same notes over here when it's a one particular atom is showing multiple, more than one valency, behaving differently with atoms under different conditions, and hence giving rise to different products, we say as variable valency. So examples of variable valencies, we are having two sorts for examples of variable valency. That means I'll not give as compounds rather over here. You can form the compounds, but variable valency is basically rather occurs with mostly for we consider for atoms of metals rather. I should say better to say metals. It also occurs variable valency for non-metals also. That's not a problem. But generally we associate with we are concerned with the metals. We are having the lower valency identified as us. When we name them, when we write the names, we can write those as two ways. For example, let's consider ferrous and ferric. So the lower valencies are always named or with the suffix us, and the higher valency ik. So whatever the name is, we remove them, and at the end, and we at the last two or three alphabets, and we use these suffixes. So one is the us, lower valency, and the higher valency is ik. And we can also write using Roman numerals. We can write ferrum 2 or iron 2 chloride, iron 3 chloride. Iron 3 chloride means ferric chloride. Iron 2 chloride means ferrous chloride. Cuprous
1 cupric 2. So the actual is cuprum. So we can write copper 1 carbonate, copper 2 carbonate, or copper 1 nitrate, copper 2 nitrate. No problem. So copper 1 is cuprous, copper 2 cupric. So based on this, we're having arsenous, arsenic. Now here is a point. This Roman numeral is mostly used under these conditions where there is a confusion. You may get confused that arsenic itself is the name of the element. Arsenic, there's no confusion with arsenas, but arsenic itself is the name of the element. And now which one? Whether I want to specify arsenic, the element itself, or I want to specify the higher valency while writing. Which one? It can be a confusion. So in such circumstances, what we normally do is we use the Roman numerals. So arsenic 5. Arsenic 5. So we write arsenic 5, that. Though there is a point that arsenic 5 compounds, I shouldn't say that means, but arsenic is acting as a metal ion. So that doesn't very rarely happen. Mostly arsenic being a non-metal, it goes into the formation of ions and gets associated with other proper metal ions, and form compounds. So arsenic is, though it is having the high valency of +5, and it's creating confusion, but still, if such situation arises, arsenic bracket Roman 5 will make us understand that what we represent, what we want to say. Stannous, stannic. Then we are having mercurous, mercuric, plumbous, plumbic. So there are many others also. These are some of the lower valencies and the higher valencies. So I hope the concept of valencies and the variable valencies have been clear to all of you. So this is what about regarding about valency, uh, what valency is all about. So if you're having any query, you may contact me and submit your questions. So for today, I'm going to stop over here. So that's all for today's lecture. Stay safe, stay at home, and take a very good care of yourself. For any queries, the contact details are there. You are free to ask questions. Till then, catch you up with some other topics in the next class. Till then, thank you so much.